alive. Okay. Excellent. I am 1 minute late. Apologies for that. All right, so stream 3. Whoa. I'm going to adjust my mic here. I think it's in a weird place where it can pick up my breath really badly. So give me 1 second. Okay, it should be better now. All right. So stream 3, the goal of the stream is to work on the Breakout environment and build a model that can solve Atari Breakout using just the images. I want to quickly go over, well, before I do that, let's go over the goals. So the goals of this particular stream are go over the results of Cartpole. I'll go over that in a second. Write a convolutional neural net that we're basically just going to copy it straight from the Atari paper. So write a convolutional net that we can use to build our model. And I was realizing that for Atari, and we'll talk about this in a second, but for Atari, it might make sense for us to crop the game image. That's something that we, in last stream, when we put together the wrapper, we didn't do this. Then I also realized that for DQN and for problems like this, often people use not the mean squared error, but rather something called the Huber loss. And we'll talk in a little bit detail what the Huber loss actually means, but essentially it's mean squared error. Hey, Michael, it's a mean squared error when the difference is small, and it becomes an absolute error when the difference is large. So we'll probably replace the current loss function with the Huber loss because it tends to be a little bit more stable. Then one of the things that I want to talk about, because Atari is a little bit more complex than Cartpole, so it might be useful. We'll start training it with epsilon greedy, but it might be useful to look at another type of exploration called boltzmann exploration, and I'll explain what that is. But essentially, it tries to reinterpret the Q values as probabilities, and I found it to converge faster, so might be good. Add a test function. We don't currently have a function that explicitly runs tests, and it's always good to have tests that run so that you can look at the actual learning. And so we need to add a function for that. And one of the other things that I'll do with that function is also make a movie as part of running the test, and then we'll log the movie to weights and biases. A couple of stretch goals. One of them is if there's time, I want to get to the point where I want to talk about how to do hyperparameter sweeps using weights and biases. And the reason I want to do that is because, especially for reinforcement learning, hyperparameters, like these things tend to be very, very sensitive to hyperparameters. The last stream was entirely about tinkering with hyperparameters, and weights and biases gives a very systematic way of testing different sets of parameters. So if there's time, I kind of want to go over that. And then something else. So like, one of the things that I'm starting to realize more and more about these streams is that you can't really, like, reinforcement learning, you set things together and you get it running, and then there's like nothing to do. So last stream when we were doing that, we set up a wrapper for the Breakout environment. This stream, if there's time, we might do something else. Maybe look at recurrent nets. Okay, so point 1. I kind of want to go over the results of the Cartpole environment. And I also want to show off, I learned how to log videos to this interface. As someone noted, I think it was Michael, that noted that if you let it train longer, it actually converges very well. So in this case, I let it run for about 2 million steps, and it was able to hit the 500 mark repeatedly in tests. I also noted that making epsilon decay relatively fast, so like it basically goes to its minimum value by about 500,000 steps, was very useful. If this was slower than that, then the learning takes a lot longer. Okay, and one of the things that I kind of want to share here, which I think is like super cool, is that if we're logging these videos, we can actually make these, where'd it go? Right here. So we can make these sort of grids of these results that, given the step in training, show you how the tests were doing over time. So here it's only like 11,000 steps and it's basically learned nothing. And then as you go over time, on the bottom here is showing the score. And as you go over time, the score gets better. I think this is not currently selecting the right run, so it's not for the run that I was demonstrating before. It goes to 500. The resolution of the animation, Matthew, or just the resolution of the screen entirely? There was a request to improve the resolution, and I'm not sure which resolution you actually mean. And I can zoom in a little bit. Anyways, so we'll go over how to do this with Breakout. Oh, and okay. For those that weren't here for last stream, we went over what the Breakout environment is. It's this game, if you haven't seen it before. The goal is to break as many tiles as possible without letting the ball hit the ground. I think there's 4 actions. There's going left, going right. There is a no op, and then there's fire. And fire is necessary to actually start the game. And I think a good goal, I don't know if we're actually going to get to a point where this is trained well by the end of the stream, but I think a reasonable goal would be to get it to, at least a score of 50 or something like that, hopefully. So with that, let's get started with the actual coding and whatnot. All right, so did that. All right. So one of the things that I think would be good to change, well, actually, it shouldn't actually matter. Yeah, so I can just make another model because this model basically has nothing to do with reinforcement learning specifically. It's just encoding a model. So we can make one separate one for convolutional nets. Now, I always like to refer to, as I mentioned in the first stream, I think, I like to refer to this deep RL tutorial by David Silver. And one of the things that this tutorial contains from the original Atari paper, there's the the convolutional net that they had used, and the example of that is here. And it's kind of funny, like the actual nature of these models changes so little from one approach to another. So this conv-net you'll see repeatedly. In a lot of different places, it would be exactly like this. So here, they were using frame stacking, which is what we're going to do as well. And they had 4 previous frames. So it's a 4-channel tensor that makes up the input. And then the size of it is 84 by 84. And then there's a single, the first convolutional layer has 8 by 8 filters and a depth of 16. And then you go to 4 by 4 filters and a depth of 32. And then there's a 256 hidden unit fully connected layer. And then you have the output. And in this case, for different problems, like they had the all 18 joystick buttons, we're not going to have that. We're only going to have 4 outputs. So let's get started on building this conv-net in Pytorch. So same thing, observation shape, number of actions, and then some learning rate. I found that learning rate of 1e to the negative 4 is better than 1e to the negative 3. Just, it's not very large. And so in the normal model, we kind of asserted that the observation shape should be, like the length of it should be 1. In this case, I think it would be good to assert that the length of the observation shape should be 4. No, 3. It should be 3. And that's basically in Pytorch, that's basically going to be the channel, and then height and width. And this is one of the differences that sometimes trips me up, at least, is that it's channel first in Pytorch. And something like TensorFlow and OpenCV, it's channel last. Okay, so we need to construct the actual net, and we can do this one as well as a sequential net. Let's get these two guys in here. Oh, it's num actions. Okay. So we got self.num actions, and then self.net equals torch.nn.sequential. Okay. So the first layer here, conv 2D. And if we look on the bottom here, I hope that's reasonably visible in the stream. But you're supposed to give it, the number of channels that you accept coming in, the number of channels that you expect going out, and then the size of the kernel, which is, I think, a length 2 tuple. And then there's a few other things like stride, padding. I don't think we're going to use any padding, etc. So the number of channels that we expect coming in this case is 4. And the number of channels that we expect going out is 16. Right. And then the number of filters, the size of the filters, or the kernel size, is 8 by 8. I think that's correct. So yeah, we have, so this represents the first convolution, and we can do the second convolution. And between this, we want to add a ReLU. So second convolution gets 16 channels coming in and 32 channels going out. And the size of the filter is 4 by 4. I think I'm missing something here. So it's not explicitly written here, but I'm reasonably sure this is supposed to have a stride of 4. And this is supposed to have a stride of 2. I just remember this from looking at an implementation of this. All this means is that this, like, it's doing an 8 by 8 convolution, but it's skipping 4 rows or 4 columns every single time. Okay, so we do the second convolution, do the ReLU, and actually, so there's 2 ways that we can go from here. In something like Keras, and I really appreciate Keras for this, Keras will look at your input shape, and then figure out how the size of that input shape changes through the model. So you don't have to be explicit about, like, you don't have to say, hey, this layer actually anticipates an input that has a depth of 4. It just figures it out. So you only have to say how many channels it's supposed to output. But Pytorch doesn't do that, and it's fine. It gives you more flexibility, and you lose a little bit of convenience for that. But in something like in a situation like this, it can get a little bit difficult to handle. Like, looking at this, knowing that our canonical input shape is 84 by 84, I could compute what the final size of this is supposed to be, but I don't want to. So I'm going to show you a trick that's very useful in Pytorch, where when you're connecting the output of some convolutional layers to a like a fully connected layer, you can sort of dynamically compute what that size is supposed to be. So let's actually do that. Let's define the forward pass for this. And in the forward pass, we can just put an IPDB. And you know what? I kind of want to put the models in a separate file. Let's do some organization. So import torch, import torch. Whoops. Okay. All right. So then down here we can say if name equals main. Let's make an instance of the conv model. And in this case, the observation shape is supposed to be 4, and then 84, 84. And then number of actions is supposed to be 4, not that that matters at the moment. And then we can create a fake tensor, so torch dot zeros, and we need to give it the batch dimension, so that's 1. The channels dimensions 4, and then you have 84 and 84, right? And then we can call m.forward with this tensor. Okay. I hope you guys appreciate my incredibly twitchy typing. Oh, and I put the models.py file in the wrong location. Okay, excellent. So let's run this file now. Torch.nn has no, modelle. Module. Oh, and I always forget that super is supposed to take in the name of the class that you're defining. It always feels kind of hacky to me the way this is done in Python, but whatever. So zoom in here a little bit. Okay, so we called the forward pass, and we ended up in that function. So let's examine x, or x.shape. 1, 4, 84, 84, as we expect. So now we can call self.net here on x, and we can look at the shape of what returns. So we get 132.99. Now, if we want to connect it to a fully connected layer, we need to see essentially what the product of this is, right? And I actually don't remember if Torch has a product function. I can just check to see, I guess, or reduce function. Oh, it does have a prod function. So yeah, so I can potentially pass, let's see, self.next x dot shape. Oh, it needs to be a tensor. So can I just turn it into a tensor? Nope. Okay, it doesn't matter. I can do this by hand. But the point here is that we can do basically this exact same thing within the initializer. So instead of just saying self.net here, I think we need to say self.convnet because that's the convolutional part. And then we can say with torch.noGrad because we don't want, we're not going to use this for back propagation, so we don't want the gradients to be calculated. And then let's just make this dummy tensor. And yeah, so in this case, the dummy actually needs to be, and let me see if that actually works. So yeah, so basically I need to add the batch dimension to this, but then I can just take the observation shape and use the star operator to construct the size of the dummy tensor. And then I can pass the dummy tensor through the convolutional net. So let's just say x equals self.convnet, pass the dummy. And then because I can be a little bit hacky here, so I can just say the like the fully connected size is supposed to be x.shape, or how about this? S is equal to x.shape. And then we can say it's S1 times S2 times S3. There's probably a lot of more elegant ways of doing this, but I think this is fine. Okay. So by doing this now, we've computed what the fully connected shapes, the size of the fully connected layer is supposed to be. And we can then go ahead and create the second part of the model. So that would be the FC net. And torch.nn. I think it's dense. No, it's not dense. Oh, it should be dense. I just did this before. Linear. It's called linear. Totally forgot. See now a moment. Okay, in features, and that's just going to be FC size. Out features, we know it's supposed to be 256. And then because society tells us to, we're just going to add a ReLU here. In features is 256. Out features is, in this case, new actions. And this defines our complete neural network. We can go ahead and test this. So let's complete our forward pass properly this time. So we're just going to, oh yeah, let's just do this lazily. So return self.fcnet self.convnet pass x. And actually, I like to just make it so that I don't have to remember to divide my input or normalize my input. So I just do it in the forward pass. By the way, I'm showing 4 concurrent viewers, but 2 people were in chat. Do I actually only have 2 viewers? Or are there actually 4 viewers? Just wondering. Okay. So let's print the forward pass, make sure that we get an actual output. Oh. And there is a size. Oh, there's a size. Of course, there's a size mismatch. I forgot to do a very important thing. So the output of the convolutional layer is, it has a shape. So convolutant has a shape of like the batch size and then 4 and 84 or 4 and 9 or whatever. Like it's a bunch of things. And we need to reinterpret this. So we need to keep the the batch dimension the same, but then we need to flatten the rest. And in Pytorch, the way to do that, I believe, is we take conv latent and call view on it. And with view, we want to... I actually don't remember this. Hang on. Let's make a tensor. And let's say batch size was 32, and then 4, and 84, and 84. And m.view, and I think it's like you need to keep 32, but then you can say -1. No. Or is it? I forgot this. Okay, I have to look this up. So Pytorch view, tensor views. Torch.view 2.8 instead of 4.4. But where's the -1? There's no -1. What? No, I did this before. Let's see. Can't just say 32. It says it's invalid for input of size 4. -1. I'm just going to look it up from another one of my repos. Let's see. Yeah. So is it supposed to be just one -1? No, that's not correct. Oh, I know what happened. I created a one-dimensional tensor. Okay, that should work better, and I can stop tearing my hair out. Yeah, so it's not 1. I'm supposed to give the batch dimension correctly. There we go. So this is just a way, this is the Pytorch way of flattening, essentially. Yeah, so I need to say x dot, or not x, conv latent dot shape 0. So we want to keep the batch dimension. And then just -1. So this will go ahead and flatten everything, which we can then pass into the fully connected net. Okay, now it should work. Models.py, there we go. So we gave it some dummy input, which is the correct size as we expect it to, and it gave us an output, which is also the correct size. So the model's working. In the it's working in the strictest sense of the word. Oh, okay, and then let's make sure it also has an optimizer, just because that's how we did it the last time. Okay, cool. So now we can go back to agent.py, make sure that it's imported. So from models, import model and conv model. Okay. So that's goal number 2 done. We have a convnet defined. Now coming down here, I kind of want to, so in an ideal world, I'd want to rewrite this so that it's, so I'm able to do different environments and it picks the model correctly, but it's like 10:30 p.m. I'm not going to do that. So instead, just take breakout v0, throw that in there. And actually we need to make a, so yeah, we wrote a wrapper for Breakout last time. And we put that in utils, I think. Yeah, there we go. So we have this frame stacking and resizing environment. And it is taking the last 4 frames, or the last whatever number that we provided frames, and it is keeping that in this buffer. And every time we call step or reset, it's basically trying to model the it's trying to model the OpenAI Gym API and just sort of serving as a wrapper on top of it. And so that it can be sort of plugged into the same kind of environment that we had before, but give a different kind of output. And in this case, the output is 4 frames of the environment stacked together. One of the things that I hadn't done for this guy was that I hadn't implemented these two. This actually should be relatively straightforward. So I think we can just do that as properties. The difference is when we get observation space.shape, we need to return the stack number, right? So we can define let's see. I don't actually know what a very good way to overload this would be. We can just have observation shape output a tensor that has the right shape. That would be the quickest way of getting this done. So let's just do that. It's ugly, but okay. So observation shape self, and we will expose that as a property. And observation shape in this case now needs to, yeah. So let's just do that. Return np.zeros, and then we can construct the shape. So that's going to be self.n, self.h, and self.w. There we go. So usually you're always going to be just taking the observation shape and calling a space and calling the shape on it. I could be like smart about this, and I could return the actual gym gym box object. But whatever, I'm not going to care about that right now. I'll probably clean this up later. Okay, so we got observation shape, and then the same thing with action space. So action space, do the same thing, return np.zeros, but actually I need to see how this is used. Okay, I'm being too lazy. Let's do the actual thing. We have gym imported already. Oh, actually don't need to do this, right? I can just return self.m.actionspace because action space doesn't matter. Okay, never mind. Yeah, I could just return this. Maybe later. Okay, so this should now at least plug in with the code that we have written in agent.py. So in agent.py, we get the environment, right? And then we get observation space.shape, so we have that now. And we also get m.actionspace.n. That's also gonna work. The last change then we need to make from utils import frame stacking and resizing environment. And so where we create the environment, we can say end is equal to frame stacking and resize environment, pass it the end itself. And it's not giving me an autocomplete here. Oh. Was it not in utils? It was in utils. Okay, it's a width, height, and number stack. So width in this case is 84, height is 84, and num stack is 4. Okay. And this, and then the other change is the model itself. So okay. So if I've done everything correctly, which I highly doubt, this should just work. I think we have, and since we're not using the DQN agent class, I don't know why I keep this around. Let's just get rid of it. So yeah, the changes that we needed to make was we changed the gem environment, we added the frame stacking and resizing environment wrapper, and we made the convolutional model, so changed that, and then everything else should just work. So what I'm going to do now, let's see. We'll talk about cropping the game image in a little bit. Oh, I didn't change the loss. Oh, somebody new in chat. Hi, I'm not going to try to pronounce your name. Ask Diatom? Okay, I did try to pronounce your name. Hi, welcome to the stream. Okay, so I do want to replace the loss with Huber loss, and I think in Pytorch it's called L1 something loss. Let's see. Smooth L1 loss for 0. No. Loss. Or Huber, maybe? Also known as the Huber loss. Smooth L1 loss. Okay. Yeah, so this is what I was talking about before. If the absolute value of the difference is less than 1, then it's MSE. And if it is greater than 1, then it is a form of it's just the absolute value minus 0.5. And I think the minus 0.5 is just there to keep continuity. And this is used for DQN a fair amount. So we're just going to replace the current loss with this guy, and hopefully that'll stabilize. I guess we will see. So that happens here. Smooth L1 loss. Let's see. So yeah, how am I supposed to use this? I've never actually used a loss function directly from Pytorch. Like, am I supposed to instantiate it and then apply it to something? Yes. Okay, never mind. I was doing this wrong. Okay. I feel like it might be we can try just constructing it every time, but that might be a little bad. Okay. So size average, what is size average? Reduction. Specifies the reduction to apply to the output. None, mean, and sum. What is the default mean? Mean is fine. Okay. I don't think we need to change anything here. So just create the loss function and then apply the loss function. And the input tensor and target tensor. So let's see. The input tensor is what? Huh? Oh yeah, it's this boy. So here's our input tensor, and that is just the, or no, it's not the summation. Why am I doing the summation? Yeah, it's just qvals times the 1 hot of all the actions. So this is the selected q values for the actions that we had chosen. That's the output of our model. And then the rewards plus. Oh no, okay, never mind. I forgot. The sum has to be done. The sum is what reduces the size to be correct. So that's the output, and then the target from the Bellman equation. Yeah, so the output from the Bellman equation is the rewards plus essentially what stands in for the max Q value that can be expected from the model in the future. So hopefully this will be fine. I guess we'll see. All right, so replace normal loss with Huber loss. That's done. And then crop game image, still gonna come to that. Just to explain what that means, in the breakout environment, the image that we're getting is this whole screen. And so some of these elements don't really contribute anything to the decision-making process, like the score. I think it's probably fine if I leave it in, but if we start seeing problems, I can crop. I'm feeling lazy. Okay. So let's get it training. Let's make sure that it works at the very least, and something happens. As that's happening, we can work on the rest of the items. So agent.py, and then I want to name this DQN breakout test. Oh, it has no object observation space. I probably named it wrong. Yep. There we go. Con model has no attribute net. I hope I'm not calling that. No, I'm not. Oh, there we go. I don't know if I can say this. If I can just say self.params, then it will get all of the parameters. Let's find out. I've never done that before. There we go. So it's doing something, and it's invisible. But we're going to spend some time in the rest of the stream making it a little bit more visible using weights and biases. Oh, and it actually failed. So this is... Where did you fail? None type object is not callable. So it failed in a forward pass? Oh, okay. I just remember. Okay, so I totally forgot that training doesn't start until we've reached 20,000 examples. So it wasn't actually training. It was just running, which is not very useful. We got 84 channels instead. Okay, so we need to change how the environment is sending its data. We didn't make it channels first. We made it channels last, and that's not going to work with Pytorch. Okay. So there's a few different ways to fix this. So this is a little bit confusing because I did define, oh no, I defined the buffer incorrectly. Okay. So we can change the shape of the buffer here. So that Noom stack is first, so then our channel's first. And when we pre-process our image, we can return a transpose or permute. Is it permute or transpose? Transpose, it's transpose. So we can return a transpose off the array rather than the array itself. So image dot transpose, and that would be do the last one first and then 0 and 1. Cool. That, I think that should be it. I don't think I have to worry about any other piece except maybe this. No, this is correct. This is as expected. Then the D stack is not correct. Okay, so that needs to change. It's a stack in the 0th dimension. Okay. Okay, cool. That should, I believe, work. Let's find out. I think for the sake of testing, I'm just going to make this smaller for now. Axes do not match array. Oh, because that's a single image. Of course, that's not going to work. So I don't need to do it here. I need to do it wherever this is being called. Okay, here. So yeah, this needs to move to the front. And then also this 0 needs to move into the front. Equals image, and same thing here. Basically just the 3rd dimension needs to go to the 1st dimension. Cool. Are you going to work now? No, it's not going to work. That's because I'm calling np.stack incorrectly because it's the axis parameter comes in 2nd, not 1st. Oh, still failed. Oh, so this is a good warning to heed. We'll get to that in a second, but there's something wrong with how we're the sizes of the arrays that are going into the loss function, so we need to fix that. That's caused me grief before. And on top of that, count 2D forward. So I guess this is happening during the forward pass. So let's use IPDB here. We're going to put ourselves in the middle there. Okay. So let's see what the size of the last observation is. Let's make sure that's all correct. 48484. Oh, okay. So there's some squeezing and unsqueezing that needs to be done, which was not necessary when we were working with Cartpole because it was just a single dimension. but it is necessary now. So if we make a tensor out of this observation, it doesn't have the batch dimension shape in there. And I think we can do that by saying unsqueeze. Yeah. So it just needs an unsqueeze before we send this over. And I don't think that should matter for when the data is actually sent to the train function, because when we send the data to the train function, we use torch.stack, and that automatically creates a dimension. So let's get rid of this IPDB. Let's run it a fourth time. I think it's the fourth time. Okay, so this seems to be working. I don't know if it can give good results because we started training really, really early. But we can still go look at it. Let's get rid of all these failed tests. Okay, so we have an average reward, we have epsilon going down, we have loss doing something. So things are moving. I don't particularly care about how well this run works. I don't know if it's actually going to work all that well. We'll find out in a little bit, I guess. But I wanted to go through some of the other tasks while this is running, so we can kind of monitor it and go through some of the other tasks. So the first thing that I want to tackle is adding a test function, because with the test function, we can start getting periodic visibility into what our model has learned. So let's move this up. I'm also going to work on logging the movie to weights and biases. Let's move this back to 20,000. I think given the size of this problem, it would be good to have a larger memory. And I totally forgot that the learning rate was set too high. So, yeah. And this is probably too soon. Just changing some hyperparameters to what worked for Cartpole at least. All right. So, test function. So what do I want from the test function? So test, or let's just do run test episode. Now, one of the things about Breakout that isn't a problem in Cartpole is the fact that a game of Breakout can get stuck in an infinite loop, and I don't think the environment provides you with any way to save yourself from that. So we're going to need to add some checks and balances for that. So run test episode. Let's give it a model. Let's give it an environment. Let's give it max steps, which we can, let's say, leave at 1,000 for now. Okay, so model, environment, max steps, and I guess we'll see if we need something more. But basically what I wanted to output is a reward, and then possibly a movie, or maybe I'll log the movie here. I haven't decided yet. So movie. Okay. And for this to work, I also need to make a change to our wrapper. So basically, at the moment, whenever we get a new image, whether it's in reset or it's in anywhere else, we are putting it through this pre-processed frame. What I want to do is, instead of holding on to just the buffer, I also want to hold on to the frame. So when we reset, get the image, but then set the frame to the copy of that image, and same thing with step, get the image. And then what I want to do is overload, because I can't expect this frame property to be present in all environments, but usually there's a render function which takes in a mode. And what I can do is say if mode equals RGB array, then return self.frame. I don't need to copy it. Okay. And then if that's not the case, then we can just pass on to the other render function. So super return whatever that returns. So now we can get access to the non-processed frame that we were getting. And this is useful for making and logging a movie. Okay. So running the test episode, one of the things that I want to figure out here is some of the... So before anything, we need to make a test environment. So we can make it the exact same way that we made environment. And now there's some similarities between running a test and doing this. But I'm gonna be messy for now. I'll figure those out later. So let's do the reset. So the observation comes from environment.reset, and then we can also say frame equals environment.frame. And we want to keep a list of frames, so let's do that. And we got the frame from the environment. So let's keep an index at 0. And then we'll say, and done equals false. We can say if not, or no, not if, while not done, and IDX less than max steps. Continue doing what you're doing. Can get the action this way. It's a little bit of code repeat, but like I said, I'll clean it up later. So get an observation, do the same stuff. Oh, device. We need to pass in the device. Okay. That gives us the action, and then we can get the, and reward. We need to be monitoring the reward as well. So get the action, get the observation reward done and nil by taking the environment and calling step with action. And yeah, so at this point, yeah, after this is done, we can get the frame. So and we can do the same thing here. Okay, so in this loop, we'll keep getting the frames, we'll keep getting the reward, and we'll keep adding it to this running reward append the new frame, get the new reward, all of that. And then once everything is done, we can return the reward itself, and then also also all the frames stacked together. Cool. So this should run a test episode, and it should return the test reward, and then also a stack of frames, and then this is what we can log to weights and biases. Okay, and to look at the training that we had started before, it really hasn't learned anything yet. Not that we've spent a lot of time here, but yeah, it hasn't learned anything. Okay. One of the other things to note here also is that this model is training relatively slowly in comparison to Cartpole, and there's a couple of different reasons for that. Probably one of the biggest one is just the fact that we have convolutions now. But we'll tinker with a few things and potentially try to get this faster as well. The target model update is probably way too quick right now. Okay, so I'm gonna keep this running at least for until we have something something worthwhile to replace it with. So let's make sure that we have a periodic test running as well. So yeah, if it's time to update the target model, and then run the test. Let's see. So run test episode, pass it the model itself, the test environment, the device, and get the reward in the frames. And then we want to log these two values, and to do that, let's look at it's like a wrapper that you need to use for the video Python library, maybe. Log function. Hey, Manas. Better late than never. One db.video? No. Log a video. Oh, whoop, there it is. I clicked the wrong one. What? I think it's just one db.video, so we'll figure it out. Hopefully the autocomplete works. Okay, so we can say 1db.log. I don't understand the question, Matthew. Weights and biases is just the name of a service that I'm using to log the data to. So that's this. It's this interface. It's kind of like an online tensor board. Okay, so 1db.log. And we have the test reward. And then test video. And I think you just do 1db.video video. And then the data is the frames themselves, the caption. We can make the caption the actual reward itself. I mean, Matthew, it is a reference to the fact that you have like a weights matrix and a bias matrix and like a standard linear neural net. I think it's a reference to that. Okay, frame rate 25 is probably fine here. Cool. So I think this should work. Going back to the training that we had started before. Again, it hasn't learned a lot, but that's okay for now. So some of the changes that we've made to the hyperparameters so far, we decreased the learning rate, we increased the memory size. I'm going to make the batch size a bit more sane. Epsilon minimum of 0.05 is fine. I'm going to slow down the epsilon decay a little bit more. Steps before train at 10 might be too early. I don't know if I should change this. Let's change it. Let's do at least 16. Okay. The rest I think is fine. Oh, I forgot that I was doing this. I think reward scaling is not really necessary for this problem. Okay, so I'm going to interrupt our present training. It's not like it's doing anything. And replace it with our new training that should start logging tests. And the tests are things that we can actually look at. So let's make sure our code is correct. I guess we're just going to sit in silence. If anyone has any questions related to what we're doing or potentially outside of it, just related to reinforcement learning or deep learning, just feel free to ask. We can have a conversation as I'm working through the remaining tasks. Okay. So going back to the tutorial, let's go ahead and visualize none of these. So here's our current run now. We haven't gotten to a test yet because the test only happens when we get to a target model update. So once we get there, we can kind of get a better idea of what's going on, potentially look at a video. Hopefully it doesn't just straight up crash. I didn't test it, which is, whoa. Yeah, I didn't test the test, so if that fails, I'm going to be sad. But it's running a little bit faster, more iterations per second than we were getting before. All right. So I'm going to call this one done. I'm going to get to the crop later. And I guess we can talk about Boltzmann exploration in the meantime. I don't know if folks in chat are familiar with Boltzmann exploration or not. But basically, and let me see if I can find a reference for it. Maybe this one. this Medium article. Here, this is a good one. So the epsilon greedy approach. So let's say that this is the output of, you know, this is the output of our neural net, and it's outputting Q values. And then the Q values are just supposed to say, hey, if you take this action, you get a reward of 0.8. And if you take this action, you get a reward of 0.55, and so on and so forth. The epsilon greedy approach says, hey, with some very small probability, I'm going to pick any action. And if that probability doesn't hit, then I'm going to pick the best action. Right? And this epsilon value, then we decay over time. Right? So as we're plotting this is sort of going down over time, and that becomes a hyperparameter. And, you know, the whole thing is just a little bit weird. I've never liked this approach. One of the approaches that I like more is when you take this idea and convert it into a probability. So now, instead of saying, I'm just going to have some blanket probability of picking any of these three actions or picking this guy, it's more, I'm going to reinterpret these values as probabilities. And in something like Pytorch, we can do this using distributions. Yeah. So we can do this using the categorical distribution. So let's get the help on that. The categorical distribution you can initialize with logits, which in this case, these would be the logits. Like we're essentially assuming them to be the log of the probabilities that we want to interpret. And then there's like a softmax operation that gives you the probabilities themselves. So we can go ahead and construct this categorical distribution and pass it as logits, a torch.tensor. And as an example, I'm going to use these values. So 0.79. 0.55, negative 0.17, and then negative 0.1. Okay. So we get a distribution, and then we can look at the probabilities. So it consumes this and creates this probability distribution. And then the idea here is that you can use, instead of using epsilon greedy, you can take your Q values, create this categorical distribution, and then use these probabilities, which is like, 40% chance that it's going to select this guy, 30% chance that it's going to select this guy, and then relatively smaller chances that it's going to select either of these other guys. And so you can then say d.sample, and that gives you an answer. So like select 2 or select 0, select 0. Sorry. So it's going to proportionately select these guys. This, to me, is a somewhat better way of exploration, at least compared to epsilon greedy. It's also very similar to, if anybody's familiar, it's very similar to the policy gradient approach, where policy gradient, the neural network itself is supposed to output a probability distribution. Here, we are just sort of faking a probability distribution, which in practice, at least in my experience, works really well. So I'm at least going to go ahead and implement it, and then we'll see how the current training is going, and we might change out epsilon greedy for this. Did it crash? No, it didn't crash. It seems like it built a file. Let's see, can we just open this? It's not there. Might have been deleted. Oh, there we go. What is this? So that was wrong. So we're not getting a test video, and the test reward is 0. Wonderful. But yeah, it's I honestly don't know what I expect here, because for a problem like this, yeah, it would need to get to like probably at least 1 million frames before we start seeing anything useful happening. Hey, Brian. All right. I'm going to let this run. I do need to figure out why the test video is so bad. I might have to look at the source code, because the documentation is kind of sparse on how you're supposed to log a video. Maybe I can go to the API. No, API examples. Nope. Reference? API reference? Apparently not. I can just go here and video. Yes, okay. Maybe I should have read this. If an umpire is supplied, we assume that the dimensions are time, channels, width, height. Ah. I gave it time, height, width, and channels. So that's on me. I guess we haven't gotten that far. Manas, yeah, larger. It's not so much larger state space. It's just much larger model. The model we had before probably had something like 100,000 parameters, something like that. This one has probably like at least 3 or 4 million. So it's just a number of like much larger number of parameters. So it's gonna train slower. It's gonna do the forward pass slower, and then on top of that, the environment might also be slower because it's having to produce images and whatnot. Hey, Lavanya, thanks for joining. So yeah, so I was passing the video incorrectly. So let's at least go ahead and fix that. All right. So test video 1db.video. We can just do the, let's see, so frames dot shape equals so time, height, width, and channels. So we want to transpose this before we pass it. Time remains time, so it's 0, and then channels, so that's 0, 1, 2, 3. Then width, which is 0, 1, 2, and then 1, 0, 3, 2, 1. So this should fix it. Whenever we restart, we should start getting, hopefully. So let's actually do this. Instead of restricting the test to the target model update, we can instead just say, we can have a separate counter for tests. So epochs before test equals, and I don't want to do it too often. Maybe we can do 500. Yeah, and then epochs since test equals 0. It's a lot of apox since test. Nope. Plus equals 1. Okay, and then if apox since test is greater than then we'll just do this. So the testing then will happen a little bit more often. It will be independent from the target model update. Cool. Let's check in on this guy. Again, like I said, before it reaches 1,000,000 frame, there's very little chance that it's going to learn anything. So we'll go ahead and kill it and start again. And we should know soon if the testing actually worked correctly. And these guys were not really useful. I can just get rid of them. Okay. So while that is happening, we can go ahead and try to introduce Boltzmann exploration. Okay. So probably the easiest way for us to do Boltzmann exploration here and actually I'm going to set that as a parameter. Okay, so by doing this, we get some output. And we can take the 0 here. And those would be our logits. We can say torch dot distributions dot categorical logits equals logits dot sample dot item. And this basically sets up Boltzmann exploration, I believe. So we can actually run, I don't think, oh, ooh, we should have a test video now. I can't catch a break. I'm gonna leave it like this. This is fine. Manas, yeah, so Boltzmann exploration actually does not, the first time I implemented it there was a lot of code because you can do it in raw NumPy and it's pretty easy to do, but it's not exactly concise. And then with torch.distributions, it's actually super nice. So I really like torch.distributions. Okay, so sorry. I guess I'll fix this for the future. What did I do wrong this time? Let's see, frames.transpose 0, 3, 2, 1. I thought I had this correct, right? It was time channels width, height width, right? And then I said keep time at time, move time height width and channels. So move channels to the second one. So I did that. So 3 goes to 2 to 1. I guess, yeah, it's this height and width that are swapped, I believe. So yeah, I guess that'll fix it. Okay. So far, again, no real learning. But we have test videos showing, which is great. What is the sample number here? Yeah, not that that matters until it actually starts doing anything useful. Is everyone's stream still smooth? I think I might be having internet issues. Let me know if the stream is having problems. Okay, so I guess Boltzmann exploration is done. Cool. I'm not gonna necessarily restart it with Boltzmann exploration. Okay, I don't necessarily understand what's going on here. That was interesting. Zach, that's weights and biases. It's not specific to Pytorch. It's just a service for logging data, and so it's like a tensor board, but on the web and has a lot more features. Yeah, I think what's going on, and I have to. Okay, yeah, I think I know what's going on. So let's look at these media files. What's the folder name? Come on. Ah. Does it get deleted? I feel like that folder gets deleted, so I can't quite examine it. I have a feeling that the GIF files that were being generated was maybe too large. I think I need to specify format. Yeah. GIF format for something like this is probably not a very good idea, just because it'll end up becoming too large, and the default is GIF, so I need to change that. Okay. So let's run this again, and this time it'll do boltzmann. Okay. So I wanted to cover more stuff, especially the hyperparameter sweep, but I'm actually really, really tired. Like it's close to midnight here, and I guess I had a more active day than I thought, so I'm kind of beat. So I'm gonna leave this running, I guess through the night. Wait. Oh my goodness. No, I can't stop yet. I love this about reinforcement learning. You make a small mistake, and then if you don't catch it, you just waste so much time. There's a problem with the size of the target vector, which we were going to fix, and I totally forgot about it. So we were computing the loss here. Let's put an IPDB there and examine the tensor sizes. It's going to take a second. How's everybody's weekend looking? $128, and then the shape of this guy. Yeah, so I did something wrong here. So what is the shape of rewards? 128, 1. And what is the shape of the mask? 128. So that's already a problem. What is the shape of this guy? 128. Okay, so I guess the problem can just be solved by saying rewards dot squeeze. Yeah, okay. Cool. And it's entirely possible that when it wasn't learning at all, it was because of that shape mismatch. Happens sometimes. Okay. So let's make sure this run is training. And then as I was saying, it's getting kind of late here, and I'm more tired than I thought I was going to be. So I think this will be it for the stream. I wanted to cover a little bit more things, but I don't think I'm going to be able to. So what I'll do instead is I'll let this train overnight, and then if it's working well, or even if it's not working well, I can make like a quick dashboard, and I'll share that at least in the, oh, I still have the IPDB. But I'll share that in the community section of the channel, and in the Discord or whatever, so folk can see. But yeah, so this is sort of at least this covers the basic setup of what changes we needed to make in order to accommodate the breakout environment. And, primarily those are having a model that can do convolutions. We went over how to deduce the shape that it needs to be before you connect it to a fully connected layer. And then we also, this was last stream as well, but this stream we also talked about how to make this frame stacking and resizing environment, and make sure that it sort of is compatible with everything, and then just how to log more data like test runs and stuff like that, so that you can get a little bit more visibility into your model. And yeah, it seems to be training now again fine. And with that, I'll say goodbye for this stream, and I'll post the results. And depending on how this turns out, the next stream will probably be about using recurrent nets with reinforcement learning. And the goal there would be to solve this exact same problem, but without frame stacking. Thank you very much for joining, for all the people that joined, and then also for any that watch this later and actually make it all the way to here. Y'all have a good night. Bye.